me say one. Alright? Okay, so look at this G. What's G? What's here? What's this one?
Graph.
A graph, yeah?
A directed graph.
Is it directed or undirected?
Directed.
Directed, yeah.
Does
Obviously,
it
I
have
have
arrows?
this. And is it weighted or unweighted?
Unweighted.
Unweighted. Because the cost between vertex is the same, right? If I put the numbers here, like 1, 2, then that's weighted, right? Because the cost from 0 to 3 is 1, from 3 to 4 is 2. You can treat it unweighted as the cost between the vertex is all 1 if there's an edge, okay? Given this directed unweighted graph. Also given a list of the start and stops. For example, like 2, 4, 1, 3. Okay, what's the sum of the shortest path between all the pairs? For example, like 2 and 4. The shortest path between 2 and 4 is, look, 2 to go to 0, 3 and 4. Then what?
That's the only way.
That's the only way. Distance is 3, right? Because 3 hops. 1, 2, 3. Okay? 3. Plus 1 to 3. 1, 2, 3. Another 3. If I add another edge, then you take this edge instead. So that will be 1. Got it? Yeah? If there's no such path, right? So for example, if 1 cannot go to 5, right? If I put a 1 to 5. If 1, there's no path between 1 to 5, then return 0. That's 0, okay?
Because there are no arrows.
Yeah. It's not connected, right? Even it's connected, sometimes there's no path because it's directed. So look, 1, 2, 2, and then 3. So there's no path between 1 to 3, right?
But can the
So will it be 0?
Sorry?
So if there's no path, will it be 0?
If there's no path, though, this bit, the cost would be, the distance would be 0. So we just need to sum up it. But put it simple, just consider this graph, directed unweighted graph. We want to find out the shortest path between any two vertex. So what kind of algorithm comes to your mind?
Breadth search.
Breadth search, yes. Breadth search may work, but you need to exhaust all the paths. That's not very efficient, remember? We also talk about the iterative deepening, yeah? Iterative deepening search, meaning that when we set the max steps equals to 1, and we do this DFS and we stop at max steps 1, and then we increment the max steps to 2, right? And then we do this depth search, and the depth search will stop when the distance exceeds the max steps. Okay, so that's the way of using the depth search in iterative deepening search to find out the shortest distance between two vertex, right? Okay, but breadth search is more straightforward, right? Because it's directed, unweighted. Because the thing is unweighted. If it's unweighted, it means that we can use the breadth search, right? But if it's weighted, then we can't use the breadth search. If it's weighted, we probably need to use the uniform cost search. Yeah, uniform cost search. We talk about that. Yeah. Dijkstra. Okay, we will talk about that. Yeah? Dijkstra. And then Floyd. We talked about that yesterday, remember? We mentioned that. Floyd Warshal. Okay? The most important thing about this Floyd Warshal algorithm is that it's a dynamic programming. So remember, we talk about this I to J. We want to calculate the shortest path between I to J. And at some point, we find the K vertex, and then we find out that distance I to K plus distance K to J is smaller than distance I to J. So what does it mean? Look, we want to find the distance, shortest distance between I to J, and then somehow we find out that I to K plus K to J is shorter, right? Don't look at this triangle. Any triangle, we have the sum of any two sides is bigger than the third one, right? Yeah, for any triangle. Look, any triangle, any two sides, the sum of any two sides is bigger than the other side, am I right? Look, any two sides, the sum of triangle, any triangle, the sum of two sides is bigger. AB plus AC is bigger than BC. It cannot be smaller than BC, right? Because the distance, the shortest distance between 2 points, A and B, the shortest distance between A and B, can you find the path that connects A and B and is the shortest?
A straight line.
A straight line. Yes, perfect. A straight line. So this is the shortest, right? And this C is somehow, not on this AB to make it a triangle, right? You just say this is the shortest. So AC plus CB must be bigger than AB, am I right?
But what if C is there?
If C is there, that's a good question. Then it's not a triangle. It's a straight line. But here, this is not triangle, right? What I'm saying is that the cost between I and J, right? We can find a shorter path by jumping to K. So I plus K, the cost maybe look 100. Now, it takes 100 to travel from I to J. The cost to travel from I to K is 50 and K to J is 20. So which one is shorter from I to J?
The top path.
Yeah, you take this, yeah, because look, 50 plus 20 is smaller than 100, right? This is what it means.
Yeah, but
So,
but this is supposed to be shorter.
no, don't confuse with this. I'm saying this is not a triangle. This is,
Yeah,
some-
but that's shorter, but and this is longer path, but this one, these path is shorter. But
Consider,
that path is
no.
short
Yeah,
as
consider
well.
traffic. Consider traffic. Look,
But what if you walk? But
no, look, we are here, yeah? We are
yeah, but
Cambridge.
20 is not the same as.
We want to go to
50.
London, right?
20 is not the same as 50 though.
Yeah, but these are basically the damn same thing.
Yeah, just let's say example.
different
I'm saying, look,
numbers.
it take 100 minutes if we go the straight way to London, right? But you might travel to other maybe what's the city, other than Cambridge and London.
Manchester.
Edinburgh.
Edinburgh. Okay, consider Edinburgh. Okay, Edinburgh. So look at it's longer.
But the Cambridge to Edinburgh is so much longer than London. It should
Okay.
be something like
Fine,
Liverpool or
Tokyo.
Manchester or
Fine,
something.
Tokyo.
No, that
Okay, so
Tokyo isn't. And besides, Tokyo is not even in the United Kingdom.
yeah,
It could
okay.
be something like Liverpool or
Liverpool.
Manchester.
Okay, so Cambridge, we want to travel to
There to
Manchester, okay? Manchester, right? So if we directly travel to Manchester, that
Yeah,
takes
but-
100 minutes. But now I'm telling you
I'm
that,
sure
okay?
Manchester is that far.
Okay,
That's inaccurate.
Cambridge to Edinburgh maybe 15 minutes, and Edinburgh to Manchester 20 minutes.
To change Edinburgh to you could change Edinburgh.
To
Like something like.
Okay.
Not fast.
what's the name any city between Cambridge and Manchester?
I have no idea.
Where's Manchester?
No, but I'm not like a.
Yeah, but where's Manchester?
But I'm not like
It's
a.
the north, the
But
west.
I'm not like a geography, but I don't know where things
Okay,
are.
but you understand
Oh,
what
I
I'm
know
saying, yeah?
There's Liverpool. There's.
But I thought Liverpool was a football team though.
No, Liverpool. Well, Liverpool play, and there is Sheffield.
Sheffield, yeah, it's okay, cool. So
It's where I was born.
yeah, you probably should. Okay, but anyway, coming back to this, the core idea of this Floyd Warshal shortest path is that we can replace the distance with the shorter one if we find a third vertex. Ik plus kj is smaller than ij. Okay, so and this diagram provides us this on cubit or ov cubit. N is the number of vertex, right? So it's a multi-source shortest path distance. What it means multi-source. What's multi-source? Multi-source means that if we perform this diagram, we can find any pair.
Edinburgh is too far away.
Any pair's distance, di, dj, we can find the shortest path between vertex I and vertex j. Okay, so we talk about this, we implement this yesterday, so we just need to implement this again. So we are given this graph is the adjacent list. Okay, adjacent list. What's the adjacent list? Look, 1, 2, 2, 1, 2, 3, and 1 to 4. And the adjacent list
Is
is
there any
the
tree?
dictionary, right? So look, 1.
Henry tree.
Yeah, 1, maybe 2 to 3 here. So 1 has the vertex edges to 2, 3, 4, right? So look, the key is at the vertex. The values is the list of vertex that it has connected to, right? And then vertex 2 connects to 3, okay? That's what it is. And we want to convert it to adjacent metric. Adjacent list, we want to convert it to adjacent metric. With this diagram, we need to assess this Dij, the cost, right? So it's better we convert it to adjacent metric. Right? So we're using this two-dimensional array to store the cost between vertex I and vertex j. So we given this n, we know this n vertex, yeah, n vertex. This is the adjacent list. Then we need to convert it to D. D is the adjacent metric. So if 0, if I equal j, else infinity, for I in range n. N is the number of vertex, right? Then for j in range n. Okay. So adjacent list, we convert it to adjacent metric. So it's like 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, like something like that, right? Something like that. It's a metric. And the diagonal, the value on the diagonal is all 1 because we consider the vertex I can travel to vertex I, okay? Right? So for example, like this value is 0, 1, 2, 3. This value, we want to access this value. This value is D row 3 column 0, 1, 2, right? So it means that there's a path between the vertex 3 to vertex 2. So vertex 3 to vertex 2. Okay, and how about this one? This is D 0, 3, right? 0, 1, 2, 3. So it means that there's a path between 0 to 3. Okay, so this is D. D is the adjacent metric. We're converting the adjacent list to adjacent metric. For K in range N, yeah? For I in range N. For J in range N. Dij is minimum of Dij and Dik plus Dkj, okay? Let me draw again. Ij, and we have a k here, right? So if we find out I to k plus k to j is smaller than I to j, then we replace the shortest path Dij with Dik plus Kij. That's what it means. Got it? Very simple. Very simple idea. The time complexity, if you look at this, ON qubit, right? We talked about the product, yeah? Cartesian product yesterday, remember? We can replace this with what? For Kij in product range n repeat equal 3, okay? So range n, Cartesian product is by itself 3 times. And then we get this tuple, Kij, which serves the purpose of this one. Okay, and then we want to calculate the sum of these. Return sum Dij if Dij, right? If Dij not equals to infinity, if there's a path, otherwise else 0, then for Ij in I don't know, in array, okay? And that will be. What have you learned today? Given
Directed graph.
a direct unweighted graph, we want to find out the shortest path. The idea of this diagram is that it's based on dynamic programming. So we want to.
Dynamic programming.
Okay, listen. Just listen. Dij is the value of the shortest path between vertex I to vertex j. So we want to calculate the shortest path between I to j, the cost. And at any point, if you find the vertex k, and then we find out that I to k, the shortest, the cost between I to k and plus I k to j is shorter than I to j, then we can replace this bit with I plus k, k plus j, okay?
So if you find the distance between I to k and k to j and find that is shorter, you can replace the distance between I to j with I to k to j.
I to k, k to j, yeah? Remember the graph, yeah?
But I was just summarizing it.
Yeah, that's good. Can you summarize again?
And anyway, you just said we could use our own words.
Yeah, use your own words. Eric,
But Ryan was summarizing it, but
Eric, can you summarize using your word? Ryan did a good job. Now your turn.
So that
okay, so you find out the cost.
Yeah, we want to find out the cost between I to J.
So I to k plus k to j. If it's which one is bigger? I to k plus k to j. Versus I to j. Just
Yeah, so basically we want to find out the minimum. Yeah, okay. The minimum of these parts, I to j and I to k, k to j. Okay. So for example, in the later, if we have another t, right? I to t, t to j. So we can get these parts instead. Okay.
100,
Yeah.
2, 4.
Yeah, exactly. That's it. Okay, the time complexity, O(n) cubic. The space complexity, O(n) square, right? Because we're using the adjacent matrix to store Dij, shortest path between any pairs. This is the multi-source shortest path, Dij. So it means the shortest path between vertex I and vertex J. Okay, that will be it for today. Bye bye.
Bye bye.
Bye bye.